I'm gonna let you guys in on a little secret. I am a trend chaser, to some extent. A lot of my videos are on topics that other people have covered. A lot of my shorts have sounds that are either popular or I think are pretty cool. This video isn't even that much different. In fact, the idea for it is taken from a video with 2.6 million views from Game Theory, and if you can recognize what this fading inward thumbnail is that I'm showing you, you might be able to recognize it. I am of course talking about the Why Minecraft Will Never End video by The Science. Now, you might be wondering, why am I bringing up a Minecraft video that was posted 3 years ago to a science YouTube channel? Well, the reason I'm bringing this up is because I want to do something similar, but not with Minecraft, rather with my actual favorite game, Automation. If you don't know about Automation, well, it's a game that I like to play a lot and post videos from for my channel, and I also tie in BeamNG Drive to it because you can export Automation cars into BeamNG Drive. Now, sometimes the cars work spectacularly, and sometimes the cars are absolutely undrivable in the game, but it doesn't matter. You can export your own custom-made creation. Whether the car you made belongs in the Sistine Chapel, a supermarket parking lot, or a swamp filled with garbage, it doesn't matter. You made it in Automation, and that's all that matters. The game lets you drive it. And this led me to ask one question. How many cars can you possibly make in Automation? We're gonna try and get close to exactly how many, and by the end of this, I'm probably going to post a Steam review saying how many cars you can make in Automation, because I think that would be pretty cool. Now, before we start with the actual math behind this, I just want to talk to you about what the Poincare recurrence theorem is. According to Wikipedia, in mathematics and physics, the Poincare recurrence theorem states that certain dynamic systems will, after a sufficiently long but finite time, will return to a state arbitrarily close to, or exactly the same as their initial state. Basically meaning that, essentially, they'll return to the state that they originally started at some time. The amount of time in which this can happen can either be very short or very long, and when I mean very long, I mean very, very long. Like, multiple universes long. And if you still don't understand, I'm just going to have an example from Game Theory's aforementioned Why Minecraft Will Never End, The Science video. Here's an example of it being used in a more practical way.
Let's, in more simple terms, go over what it is we're talking about here and what it is we're calculating. Let's say, for the sake of simplicity, we have a really tiny Minecraft world that's only 2 blocks wide, 2 blocks long, and 1 block high, meaning that we have 4 free spaces to put blocks in if we want. And let's say that we only have 2 types of blocks to work with. If we consider that a space can be empty as well, how many possible states does this game have? Well, this spot here can be empty, or it can have block 1 or block 2 in it. So there's 3 possibilities here. For the space next to it, it's the same thing. In fact, all spaces have only 3 states. And in order to calculate exactly how many states this world can be in, we have to take into account that if this space is empty, all the other spaces can have any one of 3 states as well. And that's the same for every possible combination of blocks we can put down first. And thankfully, instead of actually putting each possibility in place and counting them, we can just like very easily multiply these numbers together, 3 in this case, for each available space. 3 times 3 times 3 times 3, or more simply, 3 to the 4th power, which gives us a surprisingly large but still quantifiable and understandable result of 81.
For the example that I just showed you, 81 represents the number of combinations, or the amount of time it takes for a Poincare recurrence system, a closed system, to be completed. That is how much time it takes, whether it's in minutes, seconds, years, millennia. It literally does not matter after a certain point. But if it's after seconds, then it's a little over a minute. That's how long it would take. And on that note, I think that we can actually get started with this because there isn't that much to do. It's just doing some math, doing the calculations, and I'll explain all my calculations throughout the video. Anyway, let's go. Page 1 is the body selection page. I went through this entire page and I counted in total 3,368 car bodies is what I counted out. That is over 6 times as many as what this one answer from Reddit said. I'm gonna assume that this answer was from a much older version of the game though. For the chassis combination page, I got 147 different chassis combinations, including body panel materials, chassis type, and chassis materials. There are 5 different engine placements, 5 types of front suspension, and 8 types of rear suspension. That means for the second page, I got a total of 29,400 different combinations. Now we are finally on the engine page, which is probably one of the more complex parts of this whole equation. We have a total of 12 engine piston configurations, along with 7 materials each can be made from. Now, the engine piston sizes can be at smallest 50 millimeters and at largest 120 millimeters. But if through the family size customization, you can get them larger or smaller than that. In fact, I have actually managed to get a total of 800 different sizes from bore and 850 from stroke. There are 8 different heads and valves, and 3 different materials that the head of the engine can be made out of. That extra 150,920 that I added onto there, that is for the second engine editing page on the bottom end, bringing up our total to 206,893,209,600,000. Calculating the top end of the engine goes simply as it is 101 times 101 times 110 times 3 times 100 times 120 times 100, giving us an answer of 4,039,596,000,000. Different combinations for the top end page. For the turbos page, it goes 1.895 times 3 times 40 times 5 times 6 times 180 times 40 times 100 times 100 plus 1 for the naturally aspirated option, giving us in total 491,184,000,001 different combinations for the turbos. The next page we're dealing with is the fuel system, which was a little complicated, but I got 104 times 101 times 101 times 16 times 101 times 101 times 10. This gives us 1,731,565,072,640. The exhaust page is the last page we're going to do for our engine because the painting the engine part is going to be just added into the overall texture part of this video. But yeah, for the engine part, I got 6 times 101 times 2 times 31 times 4 times 4 times 4, which equals 2,404,608 combinations for the exhaust. And now we have to multiply all of our engine stats together, and then we'll get our answer. Our number is 50 novemdecillion. I am not reading the rest of that out because that number has 62 digits. That is way too long for me to read. For reference, that is more than the number of atoms that make up our planet. So yeah, just put that in mind. That is how many engines you can make in automation, not counting painting them, which will come later. Anyway, our next segment will be on none other than the actual car itself. We're going to be calculating the transmission, the more advanced suspension options, safety, aerodynamics, wheels, all sorts of stuff like that. That's what we're going to be doing next. The actual car calculations weren't as bad as the engine ones, but they're still pretty complicated, so hopefully we get this correct, and we're going to start off with transmissions. For my transmission calculations, I got 7 times 45 times 100 times 100 times 101 times 101 times 7 times 100, which equals 22,493,205,000,000, which is a lot. Now let's move on to wheels. For the wheels, I got 28 times 70 times 70 times 50 times 50 times 20 times 20 times 25 times 25 times 4, which equals exactly 343 trillion. Now, let's go on to the next segment, which is brakes. For the brakes, we have 20 times 52 times 100 times 20 times 52 times 100 times 100, which equals 1,081,600,000,000. Anyway, now we are on to aerodynamics. Aerodynamics was very easy, as it was 28 times 100 to the power of 4, which is exactly 2.8 billion. Now it's time for the interior, which also should be relatively easy as well. For the interior, we got 4 times 15 times 7 times 28, which equals 11,760, which is a surprisingly small answer for one of these problems, and I was pretty shocked when I saw it, but that's the answer, and now we're going to go on to safety. For our safety calculations, we have 35 times 31 times 25 times 31 times 100 times 100, which equals 8,408,750,000, which is more than there are people on Earth. And now we're going to go on to suspension, which is our last car customization page. For our suspension calculations, we have 29 times 6 times 65 times 65 times 60 times 60 times 98 times 98 times 98 times 98 times 51 times 51 times 100, which equals 63 sextillion 492 quintillion 600 quadrillion 826 trillion 628 billion 64 million, which is a crazy amount. And we are done with the car customization calculations. Now let's take all of our answers and put them all together into one giant number. Hopefully it's not something too extreme and I was absolutely wrong. The number you are looking at is 146 septenvigintillion, which has 87 digits and is about 1.5 million times larger than the estimated number of the number of atoms in our observable universe. That is car customizations, excluding engines and painting and fixtures, and we're all gonna put this together, and hopefully this does not crash Wolfram Alpha, which is what I'm using to calculate this. Anyway, on to fixtures and paint. Paint. What a monstrosity. I don't have to figure out 1 or 2 or 5 different equations. No, I have to do 17. Luckily, I don't have to do 18 because transparent doesn't have any options other than itself. So that is just +1. And you know what? This is going to be extraordinarily insane because that is a lot of math I got to do. According to the Automation Wiki, your car can be painted in 14 different colors at once. And I'm not going to go through all over 3,000 of these cars. So I'm just going to assume the answer is closer to 12 or 13. I'll just say 12 and a half. That is what I'm going to say the average number of paint colors you can have on a car at any given time. Now, for fixtures, there were no official numbers on how many different options the average fixture has, or a maximum number of options a fixture can have when it comes to being painted, so I'm just gonna assume 5. That's all. It's a dumb guess, but sometimes you just have to make them. And anyway, I have to get to the calculation in order to get all of this done. Oh, I'm sorry, I got distracted. I was drawing instead of doing my equation, but yeah, these are the answers I got. I split them into 4 different categories: high long, low long, high short, and low short. That depends on the equation I used for them. My long equation starts with the sliders, and if you've ever made a texture in Automation, you would know that the sliders can be adjusted between either 100 and 0 or 1 and 0. Turns out, a 1 to 0 slider actually has an accuracy of 1/10,000th, technically meaning a 1 to 0 slider has 10,001 combinations within it. So yeah, they can be adjusted a lot more accurately than what they do default. Now, these right here show the equations that I did in order to get my numbers, and then at the very end, I added them all up, and well, then I took that to the power of 12.5, which gave me absolutely gigantic number. And that little thing in parentheses that says 256 to the third, that is the RGB scale, and sometimes I had to multiply that twice, because some textures, you can have 2 RGB scales, so I decided to multiply that twice, because why not? Meanwhile, for the short estimates, I decided to take the number of pixels in an 8K display and multiply it by the number of colors you can have in an RGB value, because I'm gonna assume that all the textures are secretly giant 8K images that scale depending on how close you are. That's what I'm gonna take a guess on. And also, when it comes to the number of textures you can have in Automation, I am going to take a guess that low short is the closest to the real answer for one reason. I'm fairly certain that there aren't 1.98983 times 10 to the 625th power fixtures in Automation for one reason. Depending on your research, the human eye can only see between 10 and 100 million different colors, and yeah, I'm fairly certain that 1.9 times 10 to the 625th power is just a little teeny bit larger than 100 million. Now, assuming that we are going to stick with our low short estimates, then we're basically done with colors for textures and for car bodies. We're done with it. Unfortunately, since there's no official number on a fixture limit in Automation, I'm just going to have to assume that there is probably 1,000. I'm going to assume that is the limit on the number of fixtures you can have on an Automation car, which is still utterly insane. Even worse is the amount of positions each fixture has. For the sake of simplicity, I'm just going to assume it's 10,000 cubed. That is what I'm going to assume the number of positions you can have in Automation is. And that is not even including rotating, which, okay, I'm just going to assume that is 36,000 different positions you can have. So to the 100th of a degree is the accuracy of turning precision you can have for an item. I'm just going to take a guess on that. We're just going to take 36,000 cubed plus 10,000 cubed, and that's going to be our answer. These are completely made up estimates because there's no official numbers. If there were, then it would be so much easier doing this video. Also, I forgot to mention, there are 3,211 fixtures to my counting in this game. Yes, I counted them. That is the number I got. I might be a little off, but hopefully I'm close enough. And now, it is time to figure out how many paint combinations and how many fixture combinations you can have with 1,000 fixtures. And now, our total answer for fixture combinations is 1.96227 times 10 to the 32,629th power. Well, turns out this is not actually correct. I got my math wrong. Turns out it's supposed to be the number of RGB colors to the power of the number of pixels in a 2048 by 2048 display, which I just found out after doing this equation. So yeah, I'm gonna put the new equation up and give you the new answer, which is much larger than our previous one. So yeah, this will probably make things a little more complicated. But speaking of things being more complicated, this is the number we got. we got 7.31971 times 10 to the 30.3 billionth power, which is a really long number just to say, but if you were to write it out in its full form, it would be longer than the following combined. It would be longer than the Bible, the Quran, the dictionary, War and Peace by Leo Tolstoy, Moby Dick, the entire English encyclopedia, and like a bunch of other super famously long books combined. That is how long this number is. In fact, the longest piece of fiction ever written is a Loud House fanfiction that is 31.476 million words long. And even giving this fanfiction the benefit of the doubt that every single word is 9 characters plus a space long, the number we received is still so much longer. In fact, assuming our benefit of the doubt calculations, this number we received would be a little over 96 times longer than this fanfiction. That should give you an idea of just how big 30.3 billion is. That is almost 4 times larger than the number of people that live on Earth. That should give you an idea of just how big this number is. This number is so big that this number, I'm fairly certain, would take a few gigabytes of storage just writing it out. And now, let's go on to our next section, because I don't want to talk about this number anymore. And our next section is none other than names. I'm gonna assume that the first 4 have a maximum character limit of 100, and for the description, I'm gonna assume that has the maximum character limit of 10,000, because that is actually the maximum length of a YouTube comment, believe it or not. So yeah, we're gonna do the math for that, but we need to figure out how many characters you can even put in Automation. Now, Automation has 12 languages that it's available in, right here, and I did my math, and there are 10,635 unique characters that you could type into Automation. With our supposed character limit, our formula would look more like this, and you know what? We are going to multiply each and every one of them together to get a huge answer. And I did it and found out the answer is 1.1747354 times 10 to the 41,878th power. Now, if I was supposed to add all my figures together instead of multiply them, I would still get a huge number. Through addition, my exact number would be 2.3710591 times 10 to the 40,267th power, which, keep in mind, is trillions upon trillions upon trillions of times smaller than our multiplication figure. But this figure alone, that means it has over 40,000 characters to it. In fact, it is longer than some books with spaces. A book with that many characters and spaces, according to Wolfram Alpha, would be approximately 6,601 words long, which is exactly 29.46875 times longer than the Very Hungry Caterpillar. Enough with talking about the Very Hungry Caterpillar. I want to figure out what the average between these two is, because I actually do not know which one is the right answer. Running both of these through Wolfram Alpha, we get this. A truly monstrous number, 5.8736770000 repeating, times 10 to the 41,877th power. And we are done with our total equation. And you know what? Just for funsies, I'm gonna throw in a ×2 to the entire equation, because you have the option to export it to BeamNG Drive or not. That is your choice. And you know what? I'm just gonna assume half of all cars will be exported, half of all cars won't be. And with that, we are finally done with our equation, and now we can press enter into Wolfram Alpha. We are finally done. This has taken me a little while. In fact, it has actually taken me a few weeks to do this. Whether it's compiling numbers, doing the math, double checking my math, editing, it doesn't matter. We finally got it done, and I can get this question that quite literally no one asked off the top of my head. A question that I thought to myself. A question that some of you might be curious to hear, but didn't really need to know. It's just one of those curiosity questions. One of those questions that you are dying to know the answer to. That is what this video is about. Answering a question that I was truly curious about. And maybe a few other people were curious, but hopefully you like this. And today, we're gonna get the answer, and we're gonna get it soon. And now, I present to you the almighty final formula.
It's time for the moment you've been waiting for. Da 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 da
The number you are looking at is 10 to the 10 to the 10 to the 41,878.04399467167th power. A number so big that there is not enough storage in the world to display it in any of its glory. In fact, take every book ever written by all of humanity combined. Everything. This number is longer than all of them combined, and all their copies as well. This book is longer than all the text on the internet combined. This number is so big that it is physically impossible to display, and probably mentally impossible to explain as well, because this number doesn't have a physical meaning. This number doesn't mean anything in the grand scheme of things. It's just a number of combinations. Almost all the cars within this number of combinations will never, ever see the light of day. Only a very, very small fraction of a fraction of a fraction of a fraction of this number of cars will even see a chance at being exported into BeamNG Drive. And this is assuming that half of them aren't exported into BeamNG Drive. That's what that times 2 is. And everything about this number should just make you feel insignificant. This number is designed to be as big as possible. This number is probably the biggest number I have ever seen in my entire life, and I am not exaggerating when I say that. The only number that even comes close to rivaling it is the Poincaré recurrence time of our own universe, which is even larger at 10 to the 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 1.1, which is an incalculably huge amount larger than the number we got for our automation figure. I don't even think I can explain just how much larger this number is than what we got for automation. Anyway, that's kind of it. But also, the number that the Minecraft video got, which I keep mentioning, that number was 10 to the 10 to the 10 to the 1.3134, which is so much smaller than the number we got. I literally cannot even describe how much smaller this number is. This is the Minecraft number, what Austin dubbed as the Minecraft Universal Constant, which I'm gonna have to give my number a name. I'm gonna call it the Theoretic Autoplex. That is what I'm gonna call it. The Theoretical Autoplex. Because it's a theoretical number. Automation is a constantly evolving game, and that number could become incredibly outdated after a few years. In fact, it will, because there's superchargers that are going to be added into the game, and none of my math included superchargers. So yeah, hopefully when superchargers get added, I do not have to remake this video, because I am not going to, by the way, because I personally think that this game is incredible, but I don't want to go do the math all over again every time a new update happens. So this video is going to stay as it is. And anyway, that is literally all. I'm not even kidding. That is literally all. Anyway, I hope you guys enjoyed. Anyway, that's all. Bye! That Steam review I mentioned at the beginning of the video, it's up now. I got it.